Good morning everyone. In today's class we are going to discuss about solid solution mechanism and phase rules. So solid solution mechanism, here we are going to discuss about substitutional reaction. But as a substitution of anion is infrequent, as the size of anion is a larger compared to cation, so anion substitution is infrequent, so we consider cation substitutions. So when the cation is substitution occur with substitutional cation of different charges, then these four possibility will exist. If we are substituting by higher valence cation, it may result cationic vacancies or interstitial anions, or if we carried out substitution by lower valence cation, then it may result anionic vacancies or interstitial cation. Let us learn these cases one by one. Substitution by higher valence cations. So whenever we add or whenever we substitute higher valence cation, just to maintain electrical neutrality, the two possibilities occurs: either there is a creation of cationic vacancies or there will be addition of anion in the interstitial site. So these are the two cases. So the first case will be now creating cationic vacancies. So if replaceable cation of a host crystal has lower charge than a cation which is replacing, so the additional charge is needed to preserve electroneutrality by creating cationic vacancies. So we can understand this using the given example. So let us take first example. So when we add calcium chloride in sodium chloride crystal, as you can observe, in a sodium chloride crystal, sodium is +1 charged, but whatever calcium we are adding, it has a +2 charge. So if I want to maintain neutrality, I need to remove 2 Na plus ion and I can add just one calcium ion, and during this process one position of sodium will be vacant. So the formula of the solutions what we get is Na. Let me consider 2x a number of Na is removed and x number of calcium is added. So the formula of a solution is Na, this is 1 minus 2x Cax Vx. V stands for vacant cation site or empty cation site, which are x in number, Cl. So this is the formula of a solutions what we get. Similarly, when we add aluminium oxide, that is Al2O3 in MgAl2O4, in this case magnesium is +2 charge, aluminium is +3 charge. If during this addition, if some number of magnesium is replaced by aluminium, now to maintain electrical neutrality, I need to remove 3 magnesium ion and I can add 2 aluminium +3 ion. Now during this case, as you can understand, there is a creation of one valency in each such substitution. So the formula of formed solution will be magnesium 1 minus 3x, because I have to remove 3 times magnesium ion, Al, the 2 as it is, plus 2 times x which is added, Vx into O4 is the formula of a solution formed. The V, that is a vacant cation site, it has a tetrahedral void. Third example is iron oxide. As we can see here, the proportion of iron and oxygen is 1:1. But as in a nature, iron is stable even in +2 as well as +3 state. As in the given example, iron is expected to be in +2 state, but there is also possibility that iron will change to Fe+3. and to maintain neutrality I have to remove 3 Fe plus 2 ion and I can add 2 Fe plus 3 and it creates one vacancies. So the formula of iron oxide solution is Fe plus 2, remove 3x from 1, so it is 1 minus 3x, 2x will be added, Fe 3, so Fe plus 3 2x, then Vx, actually Vx means number of empty void you will get is X number, so Vx into O. It is observed that the X value lies between 0 to 0.1. A second possibility is it creates interstitial cation, means extra cation will occupy in interstitial positions to neutralize the crystal. The example of this case, number 1, yttrium fluoride. In this case, yttrium is plus 3 charge is added to calcium fluoride where calcium is plus 2 charge. So after addition, as you can see, we are replacing calcium by yttrium. So if I remove one calcium and if I add one yttrium, one positive charge will increase, and to neutralize that one positive charge I need to add one anion, that is a fluoride ion. Formula for solution formed will be calcium, I am suppose removing x number of calcium ions, so Ca1 minus x, yttrium x number is added, so Yx, F2 plus x. Similarly, if I consider uranium dioxide, in this case uranium is plus 4 state, but in nature plus 4 and plus 6 both states are stable. So if I remove one uranium ion and replace by uranium plus 6, that means there will be need of addition of 1 minus 2 charge, and that is the reason why the formula of formed compound will be U plus 4 1 minus x, U plus 6x, U 2 plus x. As the charge of each oxygen is minus 2, so only one x will come in this particular case. The second possibility is if we replace a cation with a lower charge, then these two cases are possible. It creates anionic vacancies or it creates interstitial cation. Under the creating anionic vacancies, let me consider the example zirconia, that is ZrO4, where zirconium is plus 4 state, is doped with calcium plus 2. Since we are doping with lower valence ion, so the number of positive charge increases. Now to neutralize, either I can remove anions, or if I replace one zirconium by one calcium, then the formula of the solution is Zr1 minus x and Ca(x), and the same difference of the charge, that many number of oxygen I need to remove, so O2 minus x. So this is a formula of formed solutions. This creates oxide vacancies, and these compounds are generally used in refractories. Refractory means these are the companies or these are the industries which works to prepare high temperature structures. The last type or possibility is it creates interstitial cation. To understand this, let us consider stuffed silica, that is aluminosilicate, is added to quartz, that is SiO2. In this case, the silica Si plus 4 is replaced by aluminum plus 3 and it forms stuffed quartz. The formula of formed solution is lithium X, Si1 minus x, Alx O2, where x value lies between 0 to 0.5, and this particular formed alloy is applicable to prepare a material which works in high temperature use. So phase diagram will help us to predict the condition that specifies system to exhibit equilibrium. It is a plot or a graph of temperature or a pressure against composition. It summarizes the graphical form, the temperature and composition over which certain phase or a mixture of phase exists under the condition of thermodynamic equilibrium. This rule is given by W.J. Gibbs. Generally, this phase rule is applied to only thermodynamic equilibrium condition. The phase rule given by Gibbs is P plus F equal to C plus 2, where P is the number of phase present at equilibrium. And as we know, the phase is a homogeneous and physically distinct part of system which is bounded by surface and mechanically separated from other part of system. C is the number of components needed to describe a system. A smallest number of independent variable constituent by means of which composition of each phase can be expressed. And the F stands for degree of freedom or independent variable like temperature, pressure, composition, which specifies to define the system completely. Let us discuss one component system. According to phase rule, P plus F equal to C plus 2. In a one component system, C is equal to 1, so P plus F equal to 3. At a particular stage, if only one phase is present, then the degree of freedom F is equal to 2. That means system is bivariant. If two phase present, then degree of freedom F equal to 1. So system is univariant. And if three phases are present, then F equal to 0, the system is invariant. Just to understand this, the phase diagram of water. In this phase diagram of water, in this particular diagram, lower part will be vapor state. This is a liquid water and this is ice water. So at any phase or at any plane, only one phase exists. Like if I consider this water, it is only one phase and the position of this water is changing with the two components, pressure as well as temperature. So it is a bivariant. And along the line or a boundaries between two phases, the two phase exist, so it has only one degree of freedom. And at a point O called triple point, three phase exist, so it is invariant. That means degree of freedom is equal to 0. The second one is two component system or binary system. The possible variables are temperature, pressure and composition. But as in case of solid state, the pressure variable is neglected. Thus, the phase rule will be P plus F equal to C plus 1. And in case of binary system, component C is equal to 2, so P plus F equal to 3. So using this, if one phase is present, then degree of freedom equal to 2. If two phases is present, then degree of freedom equal to 1. And three phases are present, then degree of freedom equal to 0. The example of two component systems are zinc cadmium system, which you can see in this particular screen. The last system will be three component system or ternary system. This ternary system has four independent variables: pressure, temperature and two compositions of the given component. As we are not considering here volatile component, so the pressure term will be neglected. So the modified phase rule will be P plus F equal to C plus 1, and since it is a ternary system, C component equal to 3, so P plus F equal to 4. Here three crystalline stage and liquid coexist at a fixed temperature. It represents by equilateral triangle as shown in this screen, and three component forms three corners of equilateral triangle, and temperature represents vertical axis perpendicular to plane of triangle. So this is an example of one of the three component system made by mixing of acetic acid, water and CHCl3. Thank you.